again. Been quite a while since my last video. I was working on a project involving fitting an LCD display to an older test unit, and I think it's a really cool project, and if and when I get it sorted I'll show it to you. Yeah, I put a lot of work into that, like a month and a half solid, day and night, and just burnt out and I haven't done anything for the last 2 or 3 months. But before I get on back to that project, I just want to do a couple of follow-up videos. One's for this Yaesu YC355D frequency counter. My last video also had a little puzzle about a diode that I fitted to this, so I'll get to that later in the video. But for now, first of all, I've replaced these major caps, electrodes 1, 2, 3, 4, these guys. And there's this one down here which is 0.01 microfarads, which is very low for an electrolytic capacitor. It's 600 volts, but on the schematic it's this one down here between ground and the base of these two transistors, which are part of the inverter for the DC, external DC power supply option. It does seem like it says 470 microfarads there, not 0.01. So and 470, I've got a capacitor to replace it, but 470 across there does seem rather high. So I've left that out for the moment. I've put the old one back in. It tested okay, 17 nanofarads instead of 10, but that's within spec. The only other problem that seems to be remaining is, if you look at that second digit, the 2 is a bit flaky, and if I change the frequency, the 1's okay, 2's not good, 3's not good, 4's a bit sus compared to that one. 5, also not as good as the 5 at the end. 6 is alright, 7, 8's not so good, 9 and 0. So back to the schematic, there's that second digit, and I'm hoping there's just something weak about that chip. I mean, that's all it really can be, except for the neon itself, the Nixie. If it's the Nixie I won't bother, but I think I'll try replacing that. And I've got a spare one, and also found a connector to go into the DC input socket for this thing, but not that I ever expect to use it, which is also why I'm not too worried about this capacitor. But yeah, I think I'll swap that chip out and for this guy and see if that comes good. Yeah, scrub that idea. Looking at this schematic, if we look at the parts down there, we see the drivers for the Nixies are 7441N, and that's what this chip I got to replace is. But if we look at the actual part on the board, I think that's in focus. Yeah, they are 74141s. And at the time of ordering this, there was a little voice in the back of my head that I ignored, telling me that they weren't good for Nixie type voltages, but I got it anyway. And all the usual suppliers don't have any of these, the 141s, but there are Soviet era equivalents available from quite a few places in Eastern Europe, so maybe I'll get some of them, or maybe I won't. We shall see. Anyway, onto what that diode's about. In my last video, which was just a very short one, showing the meter counting up to, well, now it's not doing it, isn't it? Counting up to 99.999 kilohertz. Come on, it's counting one more out of this oscillator. But bastard, it was working until I turned the camera on. Oh, there we go. So I don't know if you can see it there, it's pretty small, 99.999 kilohertz. And that was inspired by looking at a video by the Signal Path, where Sharia had a Hewlett-Packard frequency counter with also with Nixie displays, but it had 8 digits instead of 5. And I don't know if it was a feature of that thing or it was a mod he made, but he made it count up like that instead of just updating a static display every second. He made it show the actual counting like that, and said he thought that was pretty cool, and I agreed with him. So I wondered if I could make this thing do that. So I looked into it, and at first I had a mistaken idea of how this thing works, so I'll show you what I thought. And with that other video I provided a link to this diagram, which is not very easy to suss out how this thing works because the chips are shown as dip packages rather than as logic symbols. So I provided a link to another diagram which is also in the manual. I've added this gate up here. So this is the time-based control logic. The time-based divided chain, which is looking at the block diagram, is there's a crystal oscillator, divides it down to either a kilohertz or a hertz, and this kilohertz megahertz switch on the front of the unit selects which one becomes the gate signal, which is what goes into this here, and the signal we're measuring also goes in there, and then that goes into the counter chain, which is these chips here. And at the end of each gating period, which is either a second when we're at 1 hertz or a millisecond we're at 1 kilohertz, it transfers the contents of the counter into these latches which hold it while the counter is reset to 0 to begin counting again, and while they're holding it, of course, it goes through the decoders to the nixies. So the nixies show the count that was reached on the previous gating period. I mistakenly assumed it worked like this, that the timing control generated a 1 second gate period during which the signal was measured by the counters, and then there was a load pulse which transferred the counters into the latches, and then a clear pulse to reset the counters, and after some period of holding it for display it would open the gate again and open it for another second, and so on. And maybe Sharia's one that he used, the Hewlett-Packard device, because there's a control on the back which seems to set this display period, this hold delay. But in this one, it doesn't work like that. And if I bothered to look a bit more closely at this diagram, I would have seen it. And it's actually like this. This signal from the time base, the 1 hertz signal, goes into a flip-flop, which then generates a half hertz signal. Each of the two outputs, Q and Q bar, go high for 1 second in opposition. So there's a 1 second period during which the gate's on and we get the counter going, and then when it stops, this is high for a second and the display is held for that period. So it's really like this. We have a 1 second counting period, then a 1 second hold period, 1 second count, and the load and clear as before are triggered off that edge there. So I was originally thinking that what I'd have to do to get the functionality I wanted was something like this. Some little circuit board over here where I've got all these signals coming in and power and ground. Turns out it was much simpler than that. It was just a diode. Because if we look at these latches, which are 7475s, you just look at the truth table. When the clock is high, the outputs, Q and Q bar, just reflect whatever's on the data input, D. So it's transparent, and only when the clock goes low does it latch whatever the Q and Q bar state was. So all we have to do to make this display the counting is make these latches transparent by holding the load signal high. So here it goes high for an instance, and on the falling edge it latches whatever's in the counters. But if we just don't do that, it'll count for a second and we'll see that count. It'll just flow straight through the latches to the decoders, and then for a second when the gate is closed, on the other half of that output from the flip-flop, it'll just hold it for a second, and as long as we're happy for not being able to vary it like I first proposed, that should be fine. So all we have to do is arrange this to go high during the counting period. And if we look at this, there's the load signal that goes into the latches, and it comes off an inverter. So we want to make that high, so we want to make this low. And you can see it's just a resistor to ground and a capacitor to receive a pulse. So we can easily drive that externally without conflicting with anything else. I mean, it's only a small capacitor and a high value resistor. So all we have to do is pull that low during the counting period. And how are we going to do that? Well, while it's counting, the Q is high and the Q bar is low. So if we just connect that Q bar to this, it'll hold that low during the counting period and then go high at the end. And then these timing pulses to do the loading and latching will still occur. So it doesn't matter what that's doing really. That happens after the Q bar goes back to high. So it really doesn't matter what we're doing with this, because the load signal will do the right thing shortly afterwards. And to make sure that we don't have any problems with this affecting that, all we need is a diode, just a diode there, and it worked. We can also insert a hold delay by overriding this signal, which is also a capacitor and resistor to ground, so we could drive that. In this case, I think it has to be low to inhibit the counting, but it turns out we don't need that if we're happy for this 1 second hold time. So that's what I did. You notice if I go to a little bit higher frequency, like that's 99,909, that's the maximum frequency this can show in the kilohertz range. And of course, all this display hold stuff only applies in the kilohertz range, where the gate time is 1 second. As soon as we switch to megahertz, the gate time is a millisecond, so that it's going way too fast to see the counting. You can see sort of a bit of a shimmer happening there. So it is displaying it as it counts, but it's all over in a millisecond, so you can't see anything really. So back to kilohertz, and if I switch this thing down to hertz, like if I turn it down 1, it should be 999.8. No, I did 7. Now it's 8, 9. If I go one more to 100 kilohertz, it overflows, or should. It's counting 100,001 hertz, and the override light's not coming on, so something funny there. I don't know if it's because of my diode modification. I don't think so, looking at the diagram of how it works. Should be quite independent of that. To make it a pretty gross change, we'll make it 199 kilohertz, and that's definitely overloading now. But the overload light only flashes on, so I'm not sure what that's about. Is that because of this diode mod? Let's find out. I'll just tip it over. There's my diode. Trying to zoom in on that. You can see the overload light not working properly. And if I just snip that diode, so it's back to how it was originally. Alright, we can see the overload light not working properly, and I'll just snip the diode. And the overload's still working as it was before, and the display is back to normal. Turn it around again. Just updates every second. I would have thought that should be on for a whole second. No, maybe not, no. No, it comes on from the period between overloading and clearing, so that could be quite short. Yeah, that can only come on once it's reached 100,000, and that could be well into the second for the gating period, and then at the end of the gating period, which is going to follow very soon afterwards, it clears the counter and the overflow goes out. So yeah, that could be on for just a very short period of time, depending on whereabouts in the 1 second it reaches the overflow point. That's at 199 kilohertz, so if I turn this frequency up more, it'll overflow earlier. So I don't know what's blinking, but we're getting more of an indication of overflow. Blinks every 100 kilohertz, okay. Yeah, every time it overflows 100 kilohertz, it wraps around. So yeah, it's on only after it reaches 100,000 and until the end of the gating period when it's cleared, or when it counts up, when the last few digits count up to 0 again. This shows you how many times it's overflowing. If I whack that right up, 500 kilohertz, 1, 2, 3, 4, 5, something like that. That's actually 599.999. Yeah, that explains that. So my diode mod didn't do anything there. Now, will I leave it that way? I think it looks better, so I'll probably put that diode in more permanently. And I think that just about wraps it up for this guy. So I hope you found that mildly amusing, and I'll catch you later.